So statistical power. So statistical power is an interesting one. I think it's one of those things where you kind of forget what exactly it does. So I kind of want to go through this a little differently from the curriculum. But also know the curriculum does a full kind of explanation of this. But I just wanted to kind of give you guys a little standing point, especially because it's kind of dry. So statistical power basically is just telling us how well our test does. Essentially how many type 2 errors do we make? And essentially this little equation right here, power equals 1 minus beta. And what was beta? Type 2 errors, right? So saying how many type 2 errors we have, how many false negatives do we actually make, right? So it's kind of like essentially like because false negatives are bad, we essentially are saying power. If we have a very high number of false negatives, then our power is bad. If we have a very low number of false negatives, our power is good, right? That's kind of like how we're measuring it. That's the reasoning why we call it in power. So we want to increase power, okay? So again, what does this number mean? Okay, it ranges from 0 to 1, right? So obviously, hopefully you can see that's like, if we have our false negatives down to 0, we make no false negatives, right? Our test perfectly identifies rejecting the null hypothesis when it is in fact wrong, okay? So if we are in fact like, hey, like we don't make any, false negative claims at all, we basically reject the null hypothesis when in fact we should reject it, okay? That's our perfect score. So looking at like a power of 0, right? It's basically the opposite of this, is that we actually reject the null hypothesis almost every time, right? Even though it is in fact correct, right? Or like we should fail to reject it. So this is like the opposite of this. We get a false negative, our false negatives are 100%. Basically make all the false negatives we possibly could have, okay? So one thing to note is that power, alpha, sample size, and effect size are all related together. And so this is actually a really great visualization that the curriculum links over to. So I kind of want to show this briefly. And this is where there's a lot of different numbers going on here, but I think it does a really good job. So we talked about, for example, Cohen's D, right? Basically our effect size. So if our effect size is smaller, so I'm actually going to calculate for power. Okay, and this is usually what we have. So if we have our effect size of 0.63, if I lowered the effect size of D, what would that mean for these two distributions? This is kind of review. But if I make the effect size smaller, what should happen to those distributions? Do they get closer together or farther apart? Okay, Giovanna did the closer, yeah. So we see is that if we make our effect size smaller, right? Which makes sense, right? There's a very small difference. If the effect size is like 0, basically there's no difference between the two samples, okay? In this case, I'm just gonna make it a little bit bigger, okay? So you can see here that's our effect size. If I increase the sample size, what do we expect our distribution to look like? Do we expect it to get taller or shorter if I increase the sample size? Good, I see Hazel going up like that, right? So if I increase it to 35 and kind of reset zoom, basically gets more peaky, right? And then of course I zoom it, so it does this. But if I go over to here, we can see it much more peaked over. And that's because if our sample size is larger, right, we are more likely to get closer to the true mean, okay? So obviously if I get really close, I don't know how far this, it doesn't show, but if I get very small, like a sample size of like 4, well, that means like we could have picked anywhere across this part, okay? So I'll keep it about like at like 35, okay? Or 30. All right, and then our significance level is our alpha right here. So basically our alpha is basically saying, what is that crossover? And I'm actually going to make it into a one-tailed one test so that we can see this difference. And basically it's like when we get within this region, that basically means like, oh, we should reject the null hypothesis, right? And now this beta right here is basically saying how much are these type 2 errors, kind of the opposite, saying how many false negatives we actually have. So we can see here our null right here, and this is what we tested against. We always test against the null, right? And this right here is our alternative, okay? So this is kind of like what we like say, oh, if it's not exactly the same, we expect it to be different here. And so we can see here our type error is a 5%, so that's our alpha value right here. Our type 2 error, right, is set at 15%. That's just based on the nature of how these are connected together. So if I increase, for example, the sample size, would we expect our type 2 error to increase or decrease? Yeah. So, okay, so I saw someone, was it like this, going up? So type 2 error goes up if we increase sample size, okay? So before I do it, I'm gonna say what happens when we increase sample size. What did we see? Did it get skinnier or wider? It got skinnier, right? So if this gets skinnier, we would expect those tails to have less crossover, right? So if we increase that, we actually see there's less of that crossover. In fact, I think I made it too small, too big. You can see there's even less of that crossover on this side. So actually our type 2 error would actually go down. So our power increases, is the inverse, right? So basically by making our sample size very, very large, we're less likely to actually create those type 2 errors, okay? And then of course, if I increase my alpha, this is basically saying how many positives are we allowing ourselves, or false positive we allowed ourselves. If we have say 13% of our false positives, then obviously we're never going to get any of our type 2 errors because we're basically capturing all those false positives. But of course, if we increase or decrease our thing smaller, we get more of these false positives in here, okay? And then kind of going from here is that you can see here, I have a very high false positive rate. If I increase the effect size, so when I increase the effect size, what happened to those distributions? Did they go smaller, or did they go closer together or further apart? I think I saw further apart, right? So if I increase the effect size, I get it further apart. What would happen to our type 2 errors? Would our type 2 errors go down or increase? Go down. Good, Giovanna. All right. So we can see is like if I make these very, very, very different, there we go. If I make them very different from each other, there's a smaller chance. If I make them very small, we get a much higher false positive rate, okay, our type 2. So our power is less. And so basically this is showing you a few things. Is that one, if you want to increase your power, you increase the number of samples, right? Because then we can see basically the type 2 errors, we get less and less. So if I had like a very small effect though, if I desire a small, if we know it's a small effect, we want to increase like our sample size, for example. If we had a very large or a very large effect size, we're unlikely to make those type 2 errors. Okay, so I want you to kind of keep this in mind of this visual. I think this is a good one to show you a little bit as you're kind of proceeding, like what to do. So when we're doing statistical power and when we're calculating this, okay, we're going to see if we want to reject the null hypothesis. And we want to see, are we going to reject the null hypothesis when we really shouldn't? So what we can do, one thing I want to note on here is adding more p-values. I'm sorry, when our p-value is very close to our critical value. So if our critical value is like 0.05 and our p-value is 0.051, you're like, oh, it's so close. You're like, do I redo the test? And this is where it's like, this is where you can get in some trouble in the sense of like, if you kind of keep doing this, by chance, you're going to eventually get, you're going to accidentally reject the null hypothesis when you really shouldn't, okay? And so one thing people will do is like, well, hey, I need to increase the sample size. Let me just go get some more samples. Well, the problem is if your sample actually has some rare events in it, so that's why your p-value is actually really close to being rejected, even though it really shouldn't, you're getting these, like if I look over here, you're getting all the values that are off this far end of the spectrum over here when you really were hoping to get over here. You might sometime actually get another, if you get just one other value, you actually can increase your chances of actually getting a significant value to the point where it's like, ooh, like if you do this enough times, doing these different tests over and over and over again throughout your career, you're going to reject the null hypothesis when you really shouldn't, okay? And so what you can do on this case, and this is a little different from like how the curriculum kind of presents this, is that this is where statistical power can really come in, is that you can basically use statistical power to figure out how many samples should you have, okay? So again, this is kind of like, I'm gonna go through this a little quickly, just kind of go through it, just know it's on the notebook that I have shared, but basically our different scenarios. So one is our effect size scenarios. If we have a very, very small or a large effect, small number of points will give us a p-value to correctly reject. So for example, if our p-value is, or our effect size is very, very big, it doesn't really matter if we get things on the end. Like if we have a very, very large, like this, you can see like no matter what we do, we'll probably never cross over here. So even if we get this very, very small part, our power is going to be very good because we're never going to get a false positive. We're not going to reject the null hypothesis when we really shouldn't have. Okay, so we have a big effect. You're like, cool, this is easy. Like it doesn't really matter what I do, right? Our power is really strong. If we have a small effect, well, then we're going to have more chances of actually having false positives. So now we have a much higher chance of accidentally saying, oh no, we should reject the null hypothesis, when in reality, maybe we shouldn't, okay? So Just quickly, I just wanted to show you guys what this would look like, but I realized after the fact, this graph does a pretty good job. So, but you can see a small effect versus a big effect here. And basically it's like we might pull people from this different sample that's over on this extreme value, when in reality we hope to pull this part in here. So kind of going through that even more, did I move something? Okay, is basically one thing we saw is our sample size. So one thing we could do, if we could increase the sample size, right, we can actually make it more likely for us to actually get around the true mean. So this is actually really important. If our effect size is very large, right, we likely will actually be able to reject it as possible. But if our effect size is very small, right, we actually can increase the number of samples, right, and we probably will get our sample, as we saw like from last time, if we get many samples, right, and average those means over samples, so the mean of sample means, we actually get a very narrow part, and we're actually very close to stay at that actual true mean for each sample. So we're likely to be able to reject our hypothesis when we are supposed to. We're not getting as many false negatives. Our power has increased. And then another part is our variation. So one thing is not really shown on this graph here. If we increase the variation of our distribution, what happens, and just looking at this like one distribution, what would happen to our distribution? Would our distribution get more narrow if we increase the variation, or more wide if we increase the variation? Good, I saw Giovanna motion wide, right? So good thing I have this window so I can see your guys' faces too. But yeah, you're absolutely right. If I increase the variation, right, that means I'm not just gonna get like, oh, just around here or here, I might get anywhere across this whole spectrum, right? So you would see something closer, let's say I get a little annotation tool. I would see a distribution that would go kind of like this. That would be more variation. There's just more chances for me to go over here. So just by nature, if I increase the variation, or like say my sample has a very high deviation, would my power increase or decrease, you think? Decrease, good. So we would actually, because there's more chances to overlap. So if my sample distributions have very high variance, we're gonna have a lot of overlap. So our power is going to decrease. Okay, and that's regardless of our effect size, right? So this is where we can go through. So what this would, oops, I need my tool again to actually go through. Okay, so what we can do with this then, well, okay, so those are the three different parts. Our different variation, this is me making a little note. You can ignore this. I was trying to make a distribution note and I realized it wasn't gonna work. But anyway, so we have our different variations, right? So if we have a very high variation, we need to make sure that, if we have high variation, we likely will have a lower power, okay? So one thing to note is that different tests will actually have different powers. We only see like the t-test really and the z-tests, but you'll see there's other tests we can do. Note, however, thankfully, is that the statistical student's t-test is pretty good. Like it's at a pretty high power naturally. So we don't have to worry about it too much in that sense, but we can actually calculate it from that. And I'm not gonna show you the exact way to calculate this, because to be quite honest, it's a little complicated and we have computers. Computers are here to do this for us. And the curriculum kind of walks through like what this looks like. But the way this would work usually is you might have your data and then like have the number of samples, have all the parts, and then calculate your statistical power and say, oh, statistical power looks good, usually about 80%, which is the opposite of 20% false negatives, right? So it's like, oh, cool, 80% looks good. I mean, you could do it that way, but that tends to not be the best method to use statistical power. A better way to use statistical power is actually determining how big is my sample size? Like how big should I get, how many samples should I actually use to make sure I can do this test? And that basically says, what kind of effect size do I expect? What kind of, variation do I expect? And this might actually be something you might not know. So the first thing is that if you have old data or public data, or you have a guess for what the variation is. So for example, if you think the effect size is very small, you probably can estimate about what you'd expect. And you can use that parameters, essentially your knowledge of this data, to determine like the effect size, your mean and standard deviation, and basically get this variation of means. So, and then use a computer to solve for how many n should we have. And this is where we say, oh, statistical power of 80%. So what this would look like is basically, oh, did I have this right? Yes. Basically what you would do is say, all right, if you have data, you just basically say, all right, what's my effect size? What's my variation? And then what power do I desire, right? and usually that's 80%. And we say, okay, to determine your sample size, and say, okay, I need to have this many samples to do a good enough job, because basically we're trying to do a balance act between all 4 of these different variables. In this case, we can actually calculate n from here by essentially adjusting our significance value, our effect size, all these things. So if I want a higher power, this will actually determine what kind of sample size I need. So like that's kind of like the minimum take, okay? So that's an important part, especially if you know this part. If you don't know, there's ways you can go around this. So this is actually not said in the curriculum, but I kind of want to emphasize this because this is something you can come across, is you basically say, all right, assume a sample size. You just say, all right, I'm going to do a sample size of 10 people, right? See if that's enough. Then you say, what's our desired effect, right? What do we think the effect will be? Or, what do we want the effect to actually show? And we basically put that in and then says, okay, now we'll basically, you can calculate then for a good power, so like a power of 80%, and say, how much variation would that give? If the variation seems really wide, so like you're like, oh, like this is going to be a difference of like, let's say the height of people, like for men versus women or something like that, and your variation is like a variation of like 5 feet, it's like, well, that's a huge variation. That's unrealistic. I need to increase the sample size. So you basically keep increasing the sample size of what you would expect. And that's how you can determine how many samples you should actually get if you didn't have any idea of the data itself. Okay. And then, yes, just from the curriculum, they do some good code examples. So this is like the labs. I would strongly recommend going through that because it talks about what actually in the lab it shows like, oh, calculating the statistical power from an actual experiment. And the other one saying how many people do we actually need to get this kind of power. And that's usually what you'd want to do first. You don't usually go the other way if you can, because then you kind of don't have where to go if you don't have a good enough statistical power. You're like, oh, my test is no good. Like there's nothing to go from there. So it's usually better to actually say, all right, what do I want? And then develop that test, basically how many people you need. Okay. Any questions on the statistical power then? Cool. Thumbs up if it sounds, hope it's getting an idea. Okay. And you think of like power as like, how good is my test? How powerful is my test? Okay. And again, just to note is that some tests, we're not going to talk too much about it, but some tests are better than others, are just naturally more powerful. And usually you would calculate this not by hand, but actually from a package computer, because usually the formulas are complicated anyway. All right. So I'm going to go ahead and go to a new statistical test, Welsh's test.